The official name for this section is Experiments, Outcomes, Sample Spaces, and Events, but I think a simpler, more direct name would just be Sample Spaces and Events. What we're doing in this video is just gradually easing our way into the topic of probability. So let's define what a sample space is. The sample space is the set of possible outcomes of an experiment. So you do an experiment like flipping a coin or rolling a die. The sample space, just the set containing all the different things that can happen. An event is a subset of the sample space. So it may contain one outcome, but it may well contain multiple outcomes. So let's look at a quick example. Let's say we roll a die. So that's our experiment. That's what we're doing. And if you think about the different things that can happen, well, we're just looking at what number comes up on the die. So the different things that could happen, we could have a 1, 2, 3, 4, 5, or 6. So these are our outcomes. And if we build a set containing all these different outcomes, then that's our sample space. So sample space, just the set of all possible outcomes. Now an event is a subset of the sample space. So some examples of events would be something like rolling an even number. Each of these events we're going to represent as a set. So if we say E is the event where we roll an even number, the set E would just contain those outcomes, those even numbers, 2, 4, 6. Another example of an event, we could say event F, is that we roll something that's less than 3. So the set F would contain those outcomes that are less than 3. So what's important at this point is that if we're talking about a sample space or we're talking about some events, these objects are sets. If we're talking about the sample space, we use the letter S to represent the set of all possible outcomes. And if we're talking about an event, we usually call it capital E or capital F. So these events, E and F, will always be subsets of our sample space. So let's say we toss a coin 3 times. First thing we're going to do is we're going to write out the sample space. So this is our experiment. This is what we're doing, tossing the coin 3 times. And what we care about is the sequence of heads or tails. So when we write out the sample space, we call that capital S. And it's just going to be a set containing the different outcomes. So let's write out the different things that could happen. We could have 3 heads. We could have 2 heads, in which case we would just choose where that tail is going to come up. So there we go. We could have some situations where we just get 1 head. So we could have something like heads, tails, 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 heads, tails, 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 heads. And then there's one more possibility that would be if you get all tails. And we're just going to close the set brackets there. So that is the set of all possible outcomes, otherwise known as the sample space. So now we're going to write out a particular event called E, and we've got a description of what E is. It is at most 1 tail. So again, E is going to be a set, and what we're doing here is we're just picking out the outcomes from S that satisfy this property. So the ones with at most 1 tail. So that would actually be the first 4 outcomes that we had described in S. So you could have no tails, that would be HHH, or you could have 1 tail, in which case we'd just be choosing on which flip that's going to come up. So there would be 3 more possibilities there. So there we go, that's our set E, that's an event. And what we're aiming towards in this chapter is being able to calculate the probability of a certain event happening. So we're just warming up right now and getting comfortable with sample spaces and events. So next problem, let's say we're working at a small company that just has 4 employees. We'll call them A, B, C, D. And our experiment is that we're going to choose 2 of these employees for a project. So first thing we're going to do is write out the sample space. So sample space, we'll call that S, and it's supposed to be the set of things that can happen. So let's think about all our different ways to choose 2 of these employees. So one of the choices would be choosing employees A and B. And I think what I'm going to do is I'm going to put those guys in a set. And that's just representing the fact that order doesn't matter here. So it doesn't matter whether we choose A and B in that order or B and then A. That's going to be the same set. So that's why set brackets might be convenient there. So that's one outcome. And there are going to be a few other outcomes like that. So we could choose A and C. We could choose A and D. we could choose B and C, B and D, and we could choose C and D. And those would be all of our options there. 6 possible options or 6 possible outcomes in our sample space. So let's say the event E is that employee A is not chosen. Let's write out E. So E is just a set of some of the outcomes chosen from S. So let's specifically choose the ones where A is not selected. That would be these 3 options here. So we'll just write those ones out. So one outcome is that we choose B and C. Another outcome is that we choose B and D. And then the third possibility is that we choose C and D. So 3 outcomes in our event E, but 6 outcomes in our sample space. Let's suppose an experiment has sample space S equal to the following set. So just 2 outcomes in the sample space, 1 and 2. We want to write out all possible events. Okay, so this question is testing whether we really understand what this word event means. An event is a subset of your sample space. So if we rephrase the question, it's just saying write out all possible subsets of our sample space. Okay, so that's something that we did way back when we were talking about sets. So if we list all the possible subsets of S, one option is you get the entire set S. A couple other options would be we could choose just the element 1, or we could choose just the element 2. And then a fourth option would be if you just choose none of the outcomes in S, you would have the empty set. So 4 possible events. This set would represent, okay, both things happen. This set would represent, okay, the first thing happens, this one represents the second thing happens, and then this one represents nothing happens. So now for a new experiment, let's say we roll a red die and a blue die. So rolling both those dice is our experiment. First question is, how many outcomes are in the sample space? Well, to answer this, we could use the multiplication principle. We could think, how many options are there for the red die? And then we could think, how many options are there for the blue die? So there would be 6 options for the red die, anything 1 through 6. The and is telling us to multiply, and then 6 options for the blue die, could be any number 1 through 6. So overall, 36 different outcomes in the sample space. That's a pretty big sample space. So for these type of dice problems, we're probably not going to want to write out the sample space the long way. So I'm going to show you just a different way of visualizing this. So what we could do is we could make a little table of what's happening with the red die versus what's happening with the blue die. We could just list the different possibilities for the red die, and we could list the different possibilities for the blue die, and just create this little table or grid here. So if you wanted to be really clear about the details, you could just fill in some lines so that you can see the different outcomes. So for example, this square represents rolling a 1 on both of your dice. This square here represents rolling a 1 on red and 2 on blue. And notice that that's different than doing it the other way around. Rolling a 1 on blue and 2 on red is different. You can tell the difference between those 2 outcomes. So 36 outcomes in total, each one just represented by a little square in this table. So let's say E is the event that the 2 rolls on the 2 dice sum to 6, and we're going to write out the event E. Okay, so that's going to be a set, and we're going to just list the different things that can happen. So if you want, you can look back up at your table and figure out what your outcomes are going to look like. So if we want the rolls to sum to 6, we could have, say, 1 on red and 5 on blue, or we could have 2 on red and 4 on blue. You could have 3 on both dice. You could have 4 on red and 2 on blue, or 5 and 1. So in total, it looks like we've got 5 different possibilities. Okay, now when we write these out, it wouldn't be a good idea to just write a set, like 1, 5, because if we did that, it wouldn't be clear, is the 1 coming up on the red die or on the blue die? So a safer way to do this is to actually use an ordered pair, write it like this, and then we just need to indicate, okay, which number are we writing first? Let's agree that we're going to write red first and then blue. So your outcomes could be 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. And because we've done the labeling here, it's clear that this one means 1 on red and 5 on blue, and this one means 5 on red and 1 on blue. Now, it would be totally fine if you did your labeling the other way around. So if you said, this is blue and this is red, that's fine. Just make sure to label it so that it's clear. And that will become more important as we get into other dice problems. So I'm just going to stick with doing red on the first one and blue on the second one. Okay, so we can see that there are 5 different outcomes in the event E. So we are going to bring some set operations into the discussion in a minute. So let's just have a recap back to sets. Let's think about the union of 2 sets, E union F. What we've got here is a Venn diagram just to help us visualize that. So when you take the union of 2 sets, you're capturing all the elements that are in the first set or the second set or both sets. When you take the intersection of 2 sets, you're just capturing the outcomes that are in both sets. So in your Venn diagram, you're just shading in the regions that are common to both circles. And then third operation that we need is the complement operation. You can think of that as the not operation. So you could call this not E. You would just be shading in everything that is not in the circle for E. So you'd get the outside region and you'd also get this region here. So think or for the union, think and for the intersection, and think not for the complement. And with that in mind, we are going to do some set operations on our events. So we're continuing with the same experiment that we had in our previous example. We are rolling a red die and a blue die. And now we've got some new events to work with. So the event F is that the roll on the red die is 4. The event G is that the roll on the red die is 3 or 4, and the roll on the blue die is at least 5. So our first task is to write out F and G. So really, the question here is asking us 2 things: write out F, and then separately write out G. So F, we want to capture all the outcomes where the roll on the red die is 4. Okay, so F is going to be a set of outcomes. We said in our previous example that when you're working with dice, it's a good idea to use ordered pairs. And it's a good idea just to label which die you're describing first. So let's do it in the order red, then blue. So one of the outcomes would be 4 on red and 1 on blue. Another one would be 4, 2, 4, 3. And really what's happening here is we've got 6 options for what could happen on the blue die. Red die is forced to be 4 because that's the description of what F is. So we'd have 4, 4, 4, 5, and 4, 6. So that is our event F that contains 6 different outcomes. Okay, now let's look at event G. Roll on the red die is either 3 or 4, and the roll on the blue die is at least 5. So let's list all the different outcomes that satisfy those 2 requirements. So we've already described that we're giving the red number and then the blue number in that order. So we're going to stick with that convention. So let's think. The roll on the red die can be 3 or 4. And the roll on the blue die has to be at least 5. So we could have 3, 5. We could have 3, 6. So we've captured the possibilities where the red die is 3, and we've allowed the blue die to be either 5 or 6. And then there are a couple other possibilities where the red die is 4. So we could have 4, 5, and 4, 6. So 4 different outcomes in that event. Now we're going to practice some set operations. So we're going to find F union G. So let's remember, when we take the union of 2 sets, we're grabbing all the outcomes that are in the first set or the second set or both. So you can think of it as just throwing the 2 sets together. If any outcomes appear in both sets, you only need to write them down once. So what I might do is just write out all the outcomes from F first. So we'd have 4, 1, 4, 2, 4, 3. If you get tired of writing, you can just go ... 4, 6. So that captures all of F. And then let's look at G and see what else we've got in there. So we would also have 3, 5, and we would have 3, 6. And now we don't need to write down the 4, 5 and the 4, 6 again because they've already been written down here. So there we go. So for example, someone might ask you, okay, how many outcomes are in F union G? There are 8 outcomes in F union G. Okay, let's try one more like that just to practice our set operations. Let's find the complement of F intersected with G. So first, I would want to think about what the complement of F is. Okay, let's scroll back to the question. Let's see the description of what F was. So here was F. F is that the roll on the red die is 4. So the complement of that is that the roll on the red die is not 4. Now, let's think about what happens if we take this complement of F and we intersect it with G. Remember, intersection is like an and. So we want to look at what outcomes have the roll on the red die not being 4 and also at the same time are in G. So which outcomes would those be? Well, actually the first 2 outcomes would work. So just 3, 5 and 3, 6. And so if someone asks you how many outcomes are in the complement of F intersected with G, 2 different outcomes. So one final definition for this video. We say that 2 events, E and F, are mutually exclusive if their intersection is the empty set. Let's think of a less formal way of saying that. So the intersection of 2 sets is just which outcomes do they have in common. And if their intersection is the empty set, it means E and F have no outcomes in common. So here's a rephrasing of what mutually exclusive means. E and F have no outcomes in common. So let's say we're doing an experiment where we flip a coin 3 times. And we've got a description of 2 events here, and we want to know, are the events mutually exclusive? So event E is that we get no heads. Event F is that we get no tails. Well, first thing I would do is just write out the events, E and F, so that we can take a look at them. So if we get no heads when we flip this coin 3 times, that means we must have the single outcome, tails, tails, tails. So there's only one thing that can happen, must have tails, tails, tails. The event F is that we get no tails. So therefore there's only one thing that can happen. That would be we get 3 heads in a row. So now we're going to ask, what outcomes do E and F have in common? If we were to write down the intersection of E and F, what outcomes are in both sets? None. So E intersect F is the empty set, and we would say yes, E and F are mutually exclusive. So when we say that 2 events are mutually exclusive, there are a couple of other ways of saying the same thing. You can say they have no outcomes in common. So E and F are mutually exclusive if they have no outcomes in common. Or another way we sometimes say it is they can't happen at the same time. So events E and F are mutually exclusive if they can't happen at the same time. All right, let's do a part B and see an example of 2 events that are not mutually exclusive. So let's go back and read the question again. So our experiment is that we are flipping a coin 3 times, and the question is, are the events mutually exclusive? So what we have here is a description of 2 more events. Event F is actually still the same as part A. Event F is that we get no tails when we flip this coin 3 times. Event G is that we get at most 1 tail. So let's see if we can write out our sets G and F, and then we'll decide if they're mutually exclusive or not. So getting at most 1 tail. Okay, so that could mean no tails, or it can mean exactly 1 tail, in which case we would get to decide on which toss that tail comes up. So there would be 4 different outcomes in the event G. For the event F, getting no tails, there's just one thing that can happen. You would have to have all heads. All right, so now when we're trying to figure out whether 2 events are mutually exclusive, we're going to take the intersection. And if the intersection is the empty set, then the answer is yes. If the intersection is not the empty set, then the answer is no. Okay, so the intersection, if we look at what outcomes are the same for both sets, we're seeing HHH in both sets. So that is our intersection. So more directly, we could just say G intersect F is not the empty set. So no, the sets are not mutually exclusive. So if you want a visual on what mutually exclusive means, we'll say we have mutually exclusive events if in the Venn diagram there are no outcomes in the intersection. So that's our video on sample spaces and events. Thanks for watching.